Okay, so we're going to go into refraction of waves right now. So refractions is an example that we see at the seaside over here. All right, when you see that it's actually curving, then what else can you see is the wavelength. All right, so if you look at the diagrams in your textbook, you see this line. This is actually the wavefronts. Okay, as it gets closer towards the shore, all right, you would notice that the wavelength means the distance between two wavefronts. All right, as you notice that it gets closer towards the shore, the wavelength actually decreases. All right, the main reason is because refraction of wave has occurred. So what is refraction of wave? Refraction of wave is the change in direction of propagation of wave caused by the change in velocity of the wave when it actually propagates from one medium to another medium. So what does this actually means? It means that when a wave undergoes refraction, number one, the direction will change. Number two, it is actually caused by the change in velocity. All right, velocity will change, the direction will change due to the change of the medium. So what is the effect from the medium change? When the medium change, it actually causes the wavelength to change. If you look back at the previous notes of the lesson 2 days ago, all right, when the medium change, the wavelength of the waves will change, and when the wavelength changes, it actually causes the velocity to change. All right, the wave speed actually changes, velocity or the wave speed. And finally, this wave speed also causes the direction to change. All right, so from the definition itself, you will know what other characteristics have changed due to the refraction of wave. So here, all right, what can influence the speed of sound? As you can see at the bottom part here, the speed of sound, all right, speed of sound wave is influenced by the density of air. All right, which means the medium, the density of air will actually causes the sound wave to change. The depth of the water will influence the wave speed of the water waves. Why? Because as the depth changes, that's the medium, the wavelength of the water wave changes, therefore the speed of the water wave will change as well. All right, and then for light wave, it is actually influenced by optical density of the medium. Optical density will be explained even further and clearly at chapter 6, right, which most probably is going to be next week. All right, so please put a remark over here. This is actually what causes the wave to change when it undergoes a refraction. Okay, so this is the activity. So I'm going to show you this simulation. I have a simulation on a ripple tank right now. All right, so this is the source. This is a water wave. Okay, all right, so it's written here sound wave lah, but we can consider it as radio waves as well, sound wave water wave as well. The effect is still the same. Now what happens over here, okay, you can see that this is the source of the vibration, all right, and then the wave is actually propagating outwards, and the bright light that you see are actually the crest, the dark line is actually the throw. So what happens is that this is a circular wavefront. Now I'm gonna change it to a plane source. Okay, this is a plane wavefront. All right, so what is gonna happen here is I'm gonna stop this, I'm gonna clear the wave, and I'm gonna add a gradient, or I'm gonna add a prism over here. Let's see if I can add another thing. Okay, so I'm adding a medium here. Bring it all the way. Okay, so what we have here is we have two different mediums. All right. One is the green color one, the other one's the blue color one. So when I start the wave, you can see that between the crest, the bright fringes, that is actually your wavelength. All right, between the bright fringes, that is the wavelength. So what will happen when it actually reaches another medium? The medium will actually cause, let's just say if this is water wave, the medium will actually cause this area to change the depth of the water. So observe one thing. Number one, observe the speed. All right, how fast is it going? And also observe uh the wavelength. All right, so I'm gonna start back. Okay, so you notice this simulation over here. Right, number one, what did you observe regarding the speed of the wave? Can you please type out in the chat box? What did you observe from the speed of the wave? Did the speed actually become faster, or did it went slower? It went slower according to Ray. What about the rest? So it's obvious, you can see that this is actually moving faster and this one actually went much more slower. Even if we were to restart the simulation, all right, this is fast and then suddenly the speed started to become slower already. All right, then what about the wavelength? Wavelength is the distance between two consecutive bright, all right, two consecutive bright and here. So did the wavelength increase or did the wavelength decrease? Decrease. Good. All right. So over here, what had happened is refraction of wave happened. Right? Refraction of wave whereby just now situation is when the wave is actually moving from a deeper region to a shallow region. When you move from a deeper region to a shallow region, number one, right? The wavelength decreased. Okay, we are talking about the definition first. Number one, the wavelength actually decreased. When the wavelength decreased, the next thing that happens is that the wave speed also decreased. But I want to ask you right now, based on your knowledge that I've taught you guys previously on 2 days ago, all right, on Tuesday night, what happened to the frequency? Did the frequency change? All right, look back at the simulation. Did the frequency change? No. Why didn't the frequency change, Darren? Why, in your opinion, the frequency did not change? Why didn't the frequency change? What? Look back at the notes that you wrote previously. Yes, good. The source of the disturbance did not change. Where is the source coming from? The source is coming up from the top part. The source did not change. I didn't change the frequency over here. So when the frequency doesn't change, the source doesn't change. Therefore, the frequency is unchanged. Okay, and if you notice, we did not explain anything about the amplitude so far, so you don't have to mention regarding the amplitude. All right, we didn't measure the amplitude. Now what happens is, over here in this simulation, this is the wavefront is actually at the same direction as the source, this particular line. All right, the difference of it, what's happened? Okay, I'm going to remove this right now and I'm going to add a prism. Okay, not something I want. Hmm. Wait. Okay, never mind. I'll just use this. And I'm going to change this to a single source. And I'm going to add back the prism. Why? Because I want you guys to see what happened when it actually passes through the prism. So in order to clarify every single image, I'm just going to let it here. And I'm going to start the simulation. Look what happened at this part. When the wave comes here, all right, when the wave comes in, okay, I'm going to start narrating that lah, okay. I'm going to bring this down a little bit first because the reflection happens too fast. All right, so when the circular wave reach here, first thing, number one, when it actually hits this barrier, some of it get refracted back, reflected, all right? It get bounced back. Some of it got reflected back. But majority of it will still undergo refraction coming in here. But what happens you see is that because this line is actually in line, it's along the normal line of the circular wave fronts, when it actually cross a gradient like this, the wave now actually changes direction as though that the source is somewhere else. It doesn't go straight as what it is over here. All right. So what happens here is that when a wave, all right, when a wave propagates towards a surface or a boundary, and then when it's actually moving from a deeper region to a shallow region, the incident angle is actually more than the refracted angle. This incident angle is more than the refracted angle, means that the propagation of wave, right? The propagation moves closer towards the normal line. All right, the propagation actually moved closer towards the normal line over here. All right, so in this case, this is when deep water region, the water wave is moving from deep water region to a shallow water region. All right, the wavelength decreases, wave speed decreases, the frequency remains unchanged, but the incidence angle is greater than the refracted angle. What is incident angle? Right, this propagation of wave, all right, and this normal line, this is the incident, all right. This normal line is actually 90 degrees to the surface, 90 degrees to the boundary, all right. That's the normal line. So the angle between the propagation of the incident wave and the normal line, that is known as the incident wave, the incident angle, sorry. All right, so that is actually known as incident angle, and refracted angle is between the refracted wave line and the normal line. So the refracted wave will actually move closer towards the normal when it's moving from a deep region to a shallow region. All right, so I hope you guys wrote down the notes while I'm explaining this. When we come into light wave in chapter 6, then it will be even more clearer for you to understand. Okay, so now we'll look into shallow region moving into deep region. So for shallow region moving into deep region, all right, so in order to clarify your view, I'll just use plane wavefronts and I'll just use a medium. So I'm going to move this all the way so that the starting point is at the shallow region. All right. So what you're going to see right now is you're going to see the plane wavefront starts at the shallow region. The blue color ones are shallow. The green color one are deeper regions. So I'm going to start that. And we're going to observe again. We're going to observe the wave speed. We're going to observe the wavelength. So right now you see shorter wavelength, right? Because the distance between the circular, the brighter lines are actually much more closer to each other. All right, but when it reaches the green color area, the distance between the green lines, two consecutive green lines, they are actually further apart from each other. So this actually means that the wavelength increases, all right, when it's moving from shallow region to deeper region. Number one. Number two, when the wavelength increases, because wave speed, can I scribble here? Let's see. Right? When the wavelength increases, wave speed formula of v equals to f lambda. When the wavelength increases, the wave speed will technically increase as well because they are a directly proportionate relation. All right, but frequency will remain unchanged. All right, frequency will remain unchanged. Why? Because the source of the vibration is still the same. I didn't change the source of the vibration. Okay, so this is when we are moving from denser region to less dense region. Okay, so let me close this. Okay, and let's get back to the notes now. So when the water wave moved from shallow region to deep region, oh, here they got right already. All right, when it's moving from shallow region to deep region, number one, the incident angle is smaller than the refracted angle. So look over here. This is the incident one between the normal line, which is normal to the surface, the boundary of the shallow and the deep region, and the incident wave. So the angle between the normal line and the incident wave, that is the incident angle. The refracted angle is between the refracted wave and the normal line. So when it's moving from shallow region to deep region, it is actually that the refracted angle will be greater than the incident angle. Okay? Then the wavelength will increase as what we see in the simulation just now. The wavelength increases, but because the frequency does not change, all right, the wave speed will increase because the wavelength increases. So over here, the direction of propagation for deep to shallow, it moved towards the normal. From shallow to deep, it will refract away from the normal line. All right, so this is actually for water wave. This whole entire page at 196 is all about water wave. Okay, so now, all right, how to draw a diagram. So over here, because online and I didn't really prepare much for this, sorry. So what we see is that when the incident wave, if the question asks you to draw, all right, number one, please remember what I mentioned. This is actually a wavefront. All right. The distance between two wavefronts is what we know as wavelength lambda. Okay. So the wavelength should be the same if it's in the same medium. Then the first thing what you need to do is you need to draw the normal line. All right. You draw the normal line, dotted line first. Then after that, you draw an arrow perpendicular to the wavefronts. This arrow must be 90 degrees to the wavefronts. And then when it moved from deep region to shallow region, it should move closer towards the normal. So you don't have to measure the angle. All you have to do is, all right, what I do normally, let me see if I can screenshot this and actually bring it over to PowerPoint. Then maybe you guys can actually have a step by step on how to draw this. Right, so first thing first, what we have to do is number one, draw the dotted line, the normal. All right, so you place this somewhere here. Okay. Then that's where we draw the normal line. Oh, yeah, forgotten. Normal line is supposed to be dotted. Okay. Then after that, what we do is that we draw, make sure that the line that we're going to draw is going to be 90 degrees to the wavefront. So how am I going to consider 90 degrees? I have to consider and make sure the line here is actually in line with the wavefronts, and then when I draw that arrow, it's going to be 90 degrees. So I'm sure that most of you have already had the experience of drawing 90 degrees using a ruler inside your textbook or in your maths also. So when the incidence angle, when the wave is actually moving from deep to shallow region, technically it's supposed to move closer towards the normal. So you don't have to go and measure closer to normal. This is what I normally do. My line, my ruler is still on the lines of the incident angle. All I have to do is move this ruler so that it's moving closer towards the normal line. And then I just draw like that. No need to measure the angle. All right? Just like this. All I have to do is I just move the ruler closer towards the normal, and I consider that as refracted towards the normal line already. All right? And obviously you have to draw the line which is perpendicular, right? The wavefronts which is perpendicular. And because someone admit that, right? And because of it's actually moving from deep region to shallow region, so it's supposed the wavefronts are supposed to be closer to each other. So make sure when you measure that the wavefronts is actually very close to each other, it's straight. All right, every single distance between the lines are supposed to be same distance, equal distance. All right, so that is actually how you draw refracted waves. Okay, so let's see what else. Okay, I think this one should be okay. Now, regarding refracted of water wave, I'm gonna start scribbling here, so I hope you have your paper and pen with you. Okay. Now, one thing that how my method on memorizing refraction of wave, I will talk about the seaside. All right, the sea waves. So what we have at the sea wave is that from deep seabed all the way until the beach side. Okay, so I'm going to draw the water waves right now. Okay, this part is the deep sea area, and this is actually near the seaside where we will normally play. So what you will see is that normally when you stand at the side of the beach area, all right, you will see that when you see the places where the boats are located, the ships are located, you will notice that the ship is actually not wobbling up and down, you know. Why? Because further out at the deep sea region, the wafer are actually very far away from each other. Right? The wave are actually very far away from each other. But do you notice that as you get closer towards the seaside, the wave actually gets more and more obvious. All right? And as you get closer towards the beach, then it's going to be very, very close to each other already. All right. So what actually happened? The main reason is because sea wave is similar to water waves. All right. The one that affects whether the wavelength, all right, the wave between the sea wave, is it very close to each other or very far away from each other? It depends on the depth of the water. All right. So if the depth of the water is high, I shouldn't use the word high, is more. The depth of the water is more, which means it's much more deeper. The wavelength between two crests of the sea wave is actually very far apart. Okay, but as you get closer to the seaside, the depth actually decreases. All right, the depth actually reduces. Notice when I'm talking about the depth, I'm drawing the arrow downwards, and I'm trying not to use the verb high and low for depth. All right, so use the word more depth or less depth. Don't use lower or higher. All right, because I've already cross-checked with Mr. Sri, and also a few other English teachers throughout my experience, they did clarify that high depth means shallow, lower depth means deeper. So try not to use a confusing verb for depth. All right. So when the depth reduces at the seaside, the wavelength actually reduces as well. All right. So if the depth of water here is what D1 and here is actually D2, the wavelength over here is lambda 1, here is lambda 2. This actually means that depth 1, when the water depth at 1 is actually more than the depth at 2, the wavelength at 1 is actually greater than the wavelength at number 2. That's one thing. Then after that, because of the formula of V equals to F lambda, the wavelength right now has decreased. So the speed will also decrease as well. All right. So wave speed at 1 is actually greater compared to the wave speed at number 2. So if someone were to go to the seaside during March or April, okay, I cannot say right now because it's not a good timing to go to the beach area right now. And if you have the pelampong, the float, and you sit inside the float, when you are near the seaside, you would know that you are actually wobbling up and down. All right. But if you go further away from the sea, you feel very calm over there because you don't go up and down wobbling on the surface of the sea so much. But you have to be careful. If you're not moving up and down on the sea so much already, which means underneath here is already very, very far down. All right. So try not to move downwards after that. Okay. So this is how I memorize seawater. All right. The water wave. The closer you are to the seaside, the wavelength actually reduces. All right, the closer you are to the seaside, the depth actually reduces. The wavelength reduces, therefore, the wave speed also reduces. When you're further away out towards deep sea region, the depth of the water is actually more. Therefore, the wavelength between the two crests of the sea wave is actually greater, and the speed of wave out there is also much more greater. Okay, so that is water wave. I hope that explains. Are you guys okay with that? No problem, huh? Okay, good. Now we're gonna go to see refraction of wave right now. So you would do notice that the part that we're gonna explain right now is actually sound wave. We're not gonna explain much about light wave because light wave is in the next chapter. So in this chapter of wave, we focus mainly on sound and also sound and water waves. Okay, for reflection, diffraction, interference, I think we are going to talk about light waves. Now let's talk about sound wave. All right. During a hot day, all right, the air is closer to the surface of Earth. It's actually hotter. So when during the hot day, the air that's actually closer towards the surface is actually hotter. Why? Because the surface is actually low specific heat capacity. It absorbs heat fast, it releases heat fast as well. So the air above this is actually hot air. So the further away from the surface, it is actually much more cooler. So one thing that you have to understand is hot air means is less dense. All right, hot air is actually less dense, and then cold air are actually denser. So when the sound wave is actually coming from less dense to denser, you check back on the previous notes, all right, the notes that I explained just now. When it's moving from less dense to denser, it will refract away from the normal line. All right, it will refract away from the normal line. So when it refracts away from the normal line, the observer actually hears a very weak sound. Okay, because why? The sound is actually moving away. That's why normally when you all go to the padang, all right, and you're trying to shout at your friend to get that ball or catch that badminton racket ball or whatever it is, all right, the shuttlecock or whatever, your friend have difficulty listening to you. Why? Because when you shout, the sound from coming from you is moving from hot air upwards to colder air. So your friend can't actually hear you. But when the weather starts to become much more cooler, all right, the sun is not there, it looks like it's going to rain. And the same position you are as when the sun is out and you start shouting at your friend can hear it very perfectly clear. Why? Because during nighttime or during colder times, the lower surface is actually cold air. The upper surface is actually hot air. So hot air means again, hot air is actually less dense and cold air is actually denser. So over here, when a sound wave travels from a denser to less dense region, it will refract nearer towards the ground or closer towards the normal line. So the observer hears the sound which is actually much more louder. All right. So for those of you, if you were to experience sometimes when we were in the physics lab, you would notice that sometimes I will complain, why is it so noisy that day, especially for gamma class on Friday? Suddenly it sounds very, very noisy and loud. One of the reason is actually obviously because of during daytime on Friday, all right, it's actually very hot and almost afternoon timing already where the sun is actually very hot. So the form ones and form twos who's actually having class at the lower block, the downstairs floors at block E, when they actually talk very loud, the sound wave actually get refracted up towards the physics lab. So it is much more obvious that what we are hearing is the conversation that's coming out from the lower block of block E. All right. But when the temperature is cold, it's not that hot. All right. We can't really hear them even though that they are downstairs. But where can we hear? We can actually hear the sounds coming from upstairs. All right. Why? Because the sound from the upstairs is actually traveling downwards towards the ground. It's actually moving from colder air towards hotter air. So it will actually refract towards the ground. So this one you all can try and experience out. All right. When you go back to school or even in the holidays right now. All right. So you can identify this. And this is also the reason why we can hear things clearer at night. All right. When during the daytime, right? For example, during the daytime, if you are at the Padang, all right, when there are kids staying in the houses nearby our school, we cannot really hear them. But when the temperature is colder, all right, when the sun is not there, it's starting going to rain already, you can actually hear the kid sounds, the baby sounds, all right. So the reason is because the sound wave is being refracted, moving through either hot air or cold air. All right, so I hope this explanation will tell you guys how does sound actually refract. Okay, now with that, we're going to the next part of refraction of wave, which is quite a famous question. This question is regarding the cape and bay at the seaside. All right, at the seaside, we will have the cape region and also the bay region. So let me just quickly I want incognito. So I'm going to show you one situation right now. Okay, so what we have right now is if you look at this view, all right, when you look at this view, you have this is actually the deep sea region. I'm going to show you this. All right, this is actually the deep sea region of the Malacca Straits. Okay, so what we have here is we are going to be talking about the Cape and the Bay. So you need to identify as a physics student in terms of refraction of wave, you need to know which is the Cape and which is the Bay. All right, so Bay is actually the curving part here, and the one that comes out is actually the Cape. All right, correct, Cape, yeah. Sometimes I confuse myself also. So one place that I'm gonna search for, which is very famous for the Form 5s, this area. All right, the lighthouse at Podixon. Okay, the lighthouse at the Podixon, it is actually located at the Cape. All right, that's why it's called the Cape Racado Lighthouse. All right, this is located at the Cape region, and whereby most of the resorts and most of the hotels or motels or homestays, they are actually located more at the bay area. There is a reason why they are located at the Bay Area, and at the Cape area, this part, right, that you can see it's still mainly forest. All right. Why? Because people go to Port Dickson obviously is to go down to the seaside, but it's not safe to build a how to say a resort or a hotel facing to the towards the sea at the Cape region. All right, this is what we are trying to understand why. All right, so over here in your textbook, page 199. Okay, so this is a phenomena of refraction of sea waves. The Cape is actually shallow water region. All right, Cape is actually shallow water region, whereby the Bay is actually deep water region. So how is it considered deep and shallow? It's considered deep and shallow, which is parallel this one straight line at one condition. All right, which means that if I'm going to consider it here, all right, the deep and shallow region that I'm considering, let me just screenshot this and bring this to PowerPoint. All right, the region that they are identifying is actually here. If they considered this straight line here. Alright, if they considered this straight line here, what happens is this is the Cape. So the Cape region is actually the water is actually at the shallow region already. I hate suddenly tak boleh spell shallow. Alright, so this is the shallow region, whereby here, which is actually the bay, alright, at this region here, the bay is actually at a deeper region. Alright, so that is actually what the textbook was trying to say. At this position, one straight line here, the Cape side, this is actually shallow region, here is actually deeper region. When we look at the Google map, how do we identify it? It's actually by identifying the color. Alright, the blue color actually means that it's actually deep area. When it starts to become greenish, it's because there are sands underneath there. The depth of the seabed is actually getting less and less. All right, so that's why you can see here is a little bit greenish, but over here at the bay, it's actually blue. All right, that signifies the deeper region. Form 5, this one very familiar, right? Form 5. All right, so over here, away from the shoreline, the wave fronts of the water wave is almost straight, means that when it's initially here, right, this part, ignoring the arrow, the wave fronts are actually almost straight, right? Plain wave fronts. But when it reaches the Cape and also the Bay area, because it starts to curve, all right? When it starts to curve, the Cape will actually act as a, wait, here. Let me highlight everything easier for you all. All right. Away from the shoreline near the deep sea region, the wave fronts are actually almost straight and parallel because they are moving in uniform speed. They are the depth of the seabed is actually almost the same. But when the wave fronts of the water propagates to the cape, propagate means to move. I repeat, propagate means to move. When the wave front moves towards the cape region where it starts to become shallow, the speed of the water wave decreases because the wavelength will cause the wavelength to be shorter. So when the shallow region means the depth of the water decreases, the speed of the water wave decreases, causing the wave fronts to become shallow. And then as the water wave moves towards the bay, all right, as the wave fronts move towards approaching the bay, all right, it moves to a higher speed. It continue on with a higher speed. Why? Because it's deep sea region, it's still deep. All right, the depth of the seabed is actually still very much more compared to the Cape area. So it's still moving at high speed and the wavelength is actually longer. So this actually caused the wavefront to curve and follow the shape of the shoreline. All right, this causes the wavefront to curve and follow the shape of the shoreline. So refraction of water wave causes the water wave to converge towards the cape. Please underline and remember that. All right. And the wave will actually diverge from the bay. Converge means move towards. All right. Converge actually move towards. All right. And then diverge actually means moving away. All right. Converge means moving towards, diverge means moving away. Okay, so water wave will diverge from the bay and converge towards the cape, and it spreads out a wide region. And then this is where amplitude is being mentioned. All right, amplitude of the wave at the bay is smaller than the cape. All right, amplitude of wave at the bay is actually smaller than the cape. That's the reason why if you were to go to the Podixon at the lighthouse over there, the wave coming in, you see that the wave is actually very strong. But when you are at the Podixon, this all this hotels area, the seaside base area, you can see that the wave is actually quite small one, you know. All right, the amplitude of the wave is actually quite small. Why? Because most of the wave has already converged towards the cape. That's why the cape's wave is actually much more stronger. All right, because the amplitude is higher, the energy level will be higher as well. So the wave that hits the cape is stronger, but the wave that hits the bay is much more weaker because the amplitude has already dropped. Okay, so that is actually the explanation of refraction of sea wave. So my question is right now, should if you are a hotel developer, would you actually build your hotel at the bay or at the cape and why? Can you please answer that inside the chat box? If you are a hotel developer, will you build your hotel at the bay or at the cape? And give me answer why. Rabika, can you further explain how to keep the gas safe? You're a physics student right now answering a physics question. Try to give me an answer in physics terms. Chongwei, you never fail to actually make me laugh, Chongwei. Avdash said bay because the wave is less strong. Chongwei, best physics student. We shall see about that. Anyone have any other answers? Obviously, we will build it at the bay. Even the developers over here have already shown that it's better to build at the bay. But why at the bay? All right, because the wave is less strong. Chongwei said don't want to get sued. Chongwei, you give me the answer in the exam, I only give you 1 mark. Whether this year or next year. Xingming said, so my building will not collapse due caused by the wave. Logical answer, yes, but not a physics term answer, Xingming. Chirong says the bay has lower amplitude and would reduce the risk of the gas being swept away by the water. Bay has lower amplitude is already sufficient, Chirong. You don't have to mention that would reduce the risk of the gas being swept away by water. Honestly, to say in physics, we won't accept that last part. Xiang said because it's more safer due to deeper water region, less wave speed is produced. Xiang, your answer contradict each other. Deeper water region means that the wave speed is greater. Alright, when the wave speed is greater, So it actually contributes each other already. Pravinesh said as the speed of the water wave produced is less, thus reducing the risk of destruction of the property. Okay, can be accepted. All right, then we have, let's see, the lower amplitude at the bay, the lower the frequency. But then one thing, sorry, you know your teacher is not a Chinese student. May I know whose name is written in Chinese? Eject. Okay, but then Eject, um, you wrote the lower the frequency. You were here in my class during reflection of wave. Frequency is caused by what? What can change the frequency? Alright, you just think about that first. Harshini said, I would build at the bay because the amplitude of wave is smaller. Good, correct. Build at the Cape for Instagram aesthetic. No need lah. Rabika, you want Instagram aesthetic, just go to the lighthouse. It's already Instagrammable already. Speed, no, eject. Frequency is affected by the source. So right now, the wave is actually caused by the disturbance in the deep sea. So the frequency will not change in refraction anyway. Sharifa says base so that my guests don't die and my building is still safe. Sharifa, give me more physics answer. Brian said when the wavefront of the water propagates to the bay, the speed of the water waves increases. Not really. All right. Okay, I'm going to open the answer. Actually, the answer is inside the textbook, which I highlighted already. The main reason is, okay, why you should actually build at the bay, because water wave energy diverge away from the bay. All right. Amplitude of the wave at the bay is smaller. All right, and you can also say that the wave, here is already written what water wave energy diverge from the bay, and the amplitude of the waves at the bay is actually much more smaller. All right, so that is actually how you explain that. That's the actual answer. It's already in front of you guys. Okay, now let's see. This is the formula part. So I'm gonna use a question from the textbook to calculate and show you guys this. So I'm going to take this question to show you guys how to do the calculation. Before I actually go to diffraction of waves. All right, so here in the textbook question, figure shows a plane wavefront, plane water wave with a frequency of 10 Hz propagating from deep region to the boundary of shallow region PQ. Speed of the water wave in the deep region is 30 centimeter per second. Calculate the wavelength lambda. Okay, so I'm going to do that question first. First, number one, deep region, the wavelength, the wave speed at deep region is 30 centimeter per second. The frequency source is actually 10 Hertz. So, A, to find the wavelength, I use wave speed V equals to F lambda. So we want to find the wavelength lambda, so that would be wave speed over frequency. Should I change centimeter to meter? Actually, no need. Okay, because the question didn't ask us to do so. So what I do is 30 centimeter per second divided by frequency is 10 Hertz. 10 Hertz actually cancels out the second. So my wavelength lambda is actually 3 centimeter. All right, that is my wavelength. Now, the question says calculate the speed of the water wave in the shallow region if the wavelength in this region is 1.5 centimeter. So, what is the similarity and the differences in refraction? In refraction of wave, okay, in refraction of wave, remember the characteristic, the frequency doesn't change. And it's moving from deep region to shallow region. So the wavelength should decrease, the wave speed should decrease. With this information in mind, all right, for part B, Using the formula of V equals to F lambda, because the frequency doesn't change, so the frequency at the deep region is equals to the frequency at the shallow region, which means, rearranging this formula, the wave speed at deep region over the wavelength at deep region equals to the wave speed at shallow region over wavelength at shallow region. We want to calculate wave speed. So wave speed at shallow region equals to wavelength at shallow over wavelength at deep multiplied by the wave speed at deep region. So this is shallow region is 1.5 centimeter. Deep region, we calculated 3 centimeter times the speed of the wave speed at deep region, which is actually 30 centimeter per second. That would be 10. So answer is 15 centimeter per second. So that is how we calculate for B. Okay? All right. So I'm not going to do C here. The part D, compare frequency and wavelength and speed in the deep and shallow region. When the question asks you to compare, means you have to compare in terms of words. So the question asks us to compare frequency of wavelength in deep and shallow region. Yeah. Just going to move this. And I'm going to tell you guys how to compare. I'm just having a discussion with a bio teacher and chemistry teacher. So they are saying that students is a little bit confused on comparing in terms of biology, chemistry, and physics. So please do not mix up the method to compare in biophysics and chemistry. All right, clarify with your teachers. So the comparison, obviously, I'm giving you guys right now is actually in terms of physics. So the first question asks you to compare the frequency in deep and shallow region. So obviously, start with the word frequency of, let's just say, frequency of wave in deep region, right? The frequency, the source doesn't change. So frequency of wave in deep region is equals or is the same as the shallow region. All right, so that's comparing frequency. Then comparing wavelength. So wavelength of wave in deep region is more than the shallow region. And finally, speed. Speed of wave in deep region is more than the shallow region. Right, so that is actually how you compare in physics. We use the word more or less. All right, we use the word the same, more or less compared to the other side. All right, but I know biology is using another method. So Form 5 bio students, please go and confirm with Puantra how to do the answer properly. She just told me that Form 5 bio students go and wrote physics method in comparison. All right. So please clarify bio, physics, and chemia. When we compare something, it's three different ways of comparing. In physics, we have to say that whether is it the same or is it the more. All right. I do not know regarding biology and chemistry. You all have to go and ask bio and chemistry teacher. All right. So this is actually how we do a comparison for refraction case. All right. So up to here, refraction of wave. Are you guys okay? Hope okay, yeah. If you guys are okay, I'm gonna let my throat rest for 5 minutes. We'll come back at 9:05. Okay? All right. See you guys in a bit. Sorry, I my younger one came up for a while. Give me a few more minutes. Right, sorry about that. Okay, so we're going to talk about diffraction of waves right now. Okay. Let me catch my breath first. Okay, diffraction of wave actually happens like this when you're actually looking over here. Okay. Or another thing is I'm going to show you here right now. Okay. So this is one of bay at Port Dickson, and I'm going to zoom in. Now, bay previously we said that the wave is actually moving towards the Cape area. All right. So, but one thing is that because the wave is actually coming towards the bay here, right? So most of the energy it will actually slowly reduces, but it's still being exposed to the direct wave that's coming from the sea. So what happens here is that, okay, let me find it. Okay. So there are few stations over here you can see. Sorry, found you. That's Avian. There. You see this at this part, okay? Avian Admiral Curve. Alright, Avian Admiral Curve, what they do is they actually extended this part of the land. All right. They actually built some houses, bungalows at this area at Avian Admiral Cove. But then their main purpose was actually not to build this resorts over here or the houses over here. But the main reason is actually for this part. All right. If any one of you were to go to the Marina Condo or you go to the Admiral Marina Leisure Club, there are a lot of boats, ships, and yachts located at this area. All right. And in order for them to actually come in here, they can just leave their boat, yacht, and also small ship at these areas because it is actually protected. Right? It's protected from the exposure of the direct sea. Right? The wave when it comes in here, they are protected in here. Main reason because the opening is actually at a small part at this area. All right, this is a small opening here. So what the people actually did was they actually understand the concept of diffraction of wave. So diffraction of waves over here is actually to allow that the wave, sorry, is actually to allow the wave to spread out while propagating through the gap. So how is diffraction actually happening? So I'm just gonna pass through here for a while. Okay, diffraction's definition is at page 205. All right, it's the spreading of wave when the wave propagates through a slit or side of a barrier. All right, it spreads out. Okay, so in terms of simulation, alamak, I took out the simulation pula. All right, so I'm going to make this a plane wave. And what I'm going to do here is I'm going to add a slit. Okay, so what you can see right now is that the wave is coming. All right, there's only a small little slit over here. So technically, when a wave comes, this part is actually block area. The wave can only enter through here. But look what happened. The wave actually gets spreads out. All right, this side, the wave actually, it actually comes in here, but it actually spreads out to the areas that it's initially blocked. All right, obviously what you saw just now, there are some parts that is being reflected back, and then there's some gap and opening over here that I didn't draw this simulation properly. But we focus on the circle, the round part here. Now, what you can see is the top part here, the brightness is actually quite bright, showing that the amplitude is actually much more greater. It also shows that the energy is much more greater. All right. You would notice that, okay, the color of the mediums is up and below is still the same color, means signifying that it's actually in the same medium. When it's in the same medium, the wavelength doesn't change. It remains the same. The frequency doesn't change because I did not change here. All right. So what else changes? Let's see. When it comes in, all right, look at the speed of the wave, right? Mainly the main one over here. Don't look at the two sides one. The wave are actually the same. The wave speed are actually the same. The wavelength is also the same. So what changes? The direction changes. From a plane wavefront, it becomes a circular wavefront whereby it spreads out from the center of this opening. All right. So, and then another thing, you can see that the brightness here, the brightness of the bright color uh, pattern and the bright color lines over here signifies that the energy, all right, the energy of the wave actually decreases. All right, the energy of the wave actually decreases over here. So what happens back to the notes here? All right, for diffraction of waves, the wavelength doesn't change. Frequency doesn't change because the source doesn't change. The speed depends on the wavelength and the frequency. It's no change because frequency and wavelength is still the same. The medium is also the same. Amplitude decreases. How did we see the amplitude? From the brightness to dimmer. All right, that actually shows that the amplitude decreases. All right, the wave energy diverge and, all right, remember the word I said diverge was to spread out. So the wave energy diverge and spread out to a wider region. Direction of propagation is actually from one direction to many direction. So initially it's actually moving downwards. Right now it's actually moving downwards, moving towards the side. It's spreading out all over the place. Okay, so in this situation, because the wavefronts has spread, so this is a diffraction pattern. Okay, now I'm going to show you a few more things using this simulation. Can I? Okay, memang tak boleh. So I'm going to change this. And I'm just going to add a wall. Okay. So what happens if the opening is very big? Watch, What happens when the opening is very big? When the opening is very big, okay, you will notice that this part here, the wavefront seems to be the same, right? The brightness of the bright light, which is signifies by the amplitude, it is also the same. The only one that gets diverged away is actually this part. So this is actually a weak diffraction pattern. All right, this is a weak diffraction pattern because diffraction means you need to diverge the wave. But here, the middle part, the opening part, the wave was not being diffracted at all. It's still a plane wavefront. All right, so if you want to have a proper, nicer diffraction of wave, the opening needs to be much more smaller. All right, the opening needs to be much more smaller. All right, when it goes into a circular wavefront, this is actually what we call a good diffraction pattern. Okay, a good diffraction pattern whereby the wave is actually diverged clearer. The top part is actually because of the reflection of wave. This simulation is trying to show the whole entire real life situation. So when it actually hits a boundary, it gets reflected back. All right, that's why you have the blinking effect over there. Okay, so here, right, that is the water wave that you've seen over there. Sound wave, diffraction of sound wave is also the same thing as the explanation when I talked to you guys about the physics lab. Students, which is actually at the ground floor, we are in the physics lab, we are actually on the first floor. All right, so the wave actually get diffracted. It moves around the corner of the buildings, allowing us to hear the sound. All right, so that is actually a sample of diffraction of sound wave, or someone is talking behind the pillar and you're trying to stand here to try to peek and listen. So you hear very, very soft sound because the sound is got diffracted. Okay, this is a diffraction pattern through a single slit, all right, a light that's passing through a single slit. This is a diffraction pattern through a pinhole, all right. If we were to get a chance and enter the lab, I would show this to you. The Form 5, I think I already showed it to them previously. All right, so factors that influence the diffraction of waves. Okay, the factors that affect diffraction is whether the slit is wide or narrow, and then whether the wavelength is actually shorter or greater. Okay, so I'm just going to show you this directly. So for water wave, when the slit is wide, the center part is not being diffracted. All right, so this is actually how we draw the wavefronts. Please note that the wavefront, the distance between the wavefronts needs to be the same because the wavelength doesn't change. All right, so before and after, you need to draw the same wavelength. When it passes through a narrow slit, all right, when you pass through a narrow slit, it also gets diffracted, but this is a better diffraction pattern. It becomes more curved. Okay, then after that, shorter wavelength. If the wavelength is shorter compared to the opening, all right, then it's also not nicely diffracted. If it's a longer wavefront, then you get a curve pattern. So in a way to say for memorizing purposes, if the pattern of the wave after passing through a slit is circle, all right, circular wavefronts, it means that it's a well diffracted wave. But if you see almost straight like this is actually not a good diffraction pattern. Okay, so that is for diffraction. All right, diffraction of wave influenced by the size of the slit and the wavelength. So the effect of diffraction of wave for a fixed wavelength, if you use a wide slit size, the size of the opening is very big, it will spread less significant or lesser diffraction pattern. If the size of the slit is narrow, then the spreading of wave is more significant. Okay, more obvious diffraction pattern, more circular. If the wavelength, they fix the size of the slit, but the wavelength is shorter, all right, the spreading of wave is actually less significant, less diffraction pattern. But if the wavelength is longer, the diffraction pattern will be more obvious. They actually summarize this table over here. All right, that is what it's summarized out. Now, diffraction of wave in daily life. My conclusion over the past 2 years in KSSM, they talk about the question that they come out with is very application based. All right, so try to identify from the question what they are trying to tell you. Okay, so diffraction of wave for water wave. All right, the diffraction of water wave produces calm of water regions suitable for docking of ships and water recreational activities. That's why at some areas they'll actually put a barrier over there so that it's calm region. So let's go back and look at the map of Port Dickson. All right, so they actually put a bank over here so that people can actually put their ship and yacht over there. And then one more place I noticed just now. Where is it? All right, this is a power station, and a power station, you would see that they have this line over here. This is actually a road. So they are actually protecting the power station from the sea. All right, the energy that's coming in from the sea with the opening over here. All right, so this is actually one of the diffraction of water wave. Diffraction of water wave in real lives. All right, then we have light wave. Light wave is actually holograms produced by the effects of diffraction of light are used to make it as a safety features on the bank cards, such as debit cards and also credit cards. Sound wave, infrasonic wave produced by elephants have long wavelength to facilitate long distance communication between the elephant. So the sound that is produced by the elephants have long wavelength, right? That's the reason how between elephants, they can actually communicate between them. Okay, so that ends diffraction of wave. So what I'm going to go right now, I'm going to go into last year trial question. All right, this is last year trial question. Okay, so what I'm gonna do here is, okay, wait, I'm gonna convert this very quickly. What is my time right now? Okay, I'm gonna convert this very quickly into the Telegram. Sorry, into PowerPoint, so that we can analyze this a little bit better. So we're just going to use the chat box in the Google Meet to discuss the question, all right? Okay, I prefer to compare the whole question like this. Okay, so I'm going to start over here first. Okay, I'm going to put my PowerPoint here, this one here. Can you all see the question?
Can you zoom in, Che?
Sorry?
Can you zoom in, Che?
Still
It's
not very
better
clear, is it?
now. Uh,
Really? Okay. I'll just use this then. Okay, so I'm just going to use this. For information, those of you who's actually using handphones or tablets, you can actually pinch out and you can see, you can zoom in already, all right? All right, so here, okay, diagram 6.1a and 6.2a shows a design of a circular wave generator machine being tested. A dipper is attached to the vibrator to vibrate at a frequency of 90 Hz and 60 Hz. Now, one keyword for you guys, number one, this is a circular wave generator. There's only one chapter that will talk about circular wave generator, and that is the wave chapter. All right. And they said that the dipper is attached vibrating at 90 hertz and 60 hertz, respectively. So the first diagram, it's vibrating at 90 hertz. The second diagram is vibrating at 60 hertz. Okay. The dipper is placed on the surface of the water of a water reservoir. All right. And then diagram 6.1a and 6.2a shows a surface of the circular wave produced when the dipper hits the surface of the water. Okay, so as you can see, the water level, you can actually try to measure. The water level looks the same to me. My habit in exam, when it's talking about wave, is relating to water. The first thing that you need to know is that the depth of water can affect, all right? But here, the depth is the same. What they change is actually the frequency. All right. So when the frequency change, this is the wavefront. So what happens here is that the wavelength is actually less at 6.18. and the wavelength at 6.1b is actually greater. When the frequency is higher, the wavelength is less. When the frequency is lower, the wavelength is actually higher. Okay, so now I'm going to go to the next question. Underline the correct answer to complete the sentence below. A wavefront is a line that connects all points that have the same phase or velocity. Please answer inside the chat box. A wavefront is a line that connects all points that have the same phase or same velocity. Searching back for answer. 1, 2, 3, 4. 4% answering velocity, 5% answering velocity. My answer to you is that wrong. A wavefront is a line that connects all points that have the same wave phase. All right, same phase means same position. So all of it is at crest, all right, the maximum position. So they are actually a wavefront. All right, it's actually the same phase. Now next, compare the depth of water in the reservoir. Just now we already did try to compare that, and we actually says that how to answer this question in physics. Compare the depth of water based on diagram 6.1 and 6.2. So the method to compare is depth of water. No need to write in reservoir. Depth of water is sufficient for me. Depth of water in diagram 6.1 is the same as diagram 6.2. Okay? Then next, compare the frequency of the dipper. I remember just now the frequency of the dipper, 6.1 is more than 6.2. Okay? So I'm going to talk all about 6.1 comparing to 6.2. So I'm going to say frequency of dipper in diagram 6.1 is more than diagram 6.2. So that's how we answer in physics. Okay, compare the wavelength of the circular wave. So I remember just now that 6.1 is actually shorter. So wavelength of wave in diagram 6.1 is shorter than diagram 6.2. Okay, and then finally, question asked to relate the frequency of the dipper to the wavelength. That's the reason why I compare 6.1 and 6.1. Because here, when I relate the frequency of the dipper in 6.1, it's more. But the wavelength of the wave in diagram 6.1 is actually shorter. So I will say as the frequency increases, I use back the word in the question, wavelength. The wavelength decreases. You can also answer as the frequency of the dipper becomes more, the shorter the wavelength of the circular wave can, no problem. All right. Please do take note again, once again, the word relate can also ask you to deduce a relationship or yeah lor, either give the relationship, relate, or deduce the relationship of the frequency and the wavelength. You need to use the word increase and decrease. We cannot accept directly proportionate, inversely proportionate, linearly increasing, or linearly decreasing in this kind of question. All right. Honestly, to tell you one thing, I'm summarizing for the lesson already. In exam, for me, this kind of question of comparing is a easy mark for students. All right. Why is it easy? All you have to do is just look at the question and then you compare what the question asks and you state which is more and which is less. So by stating which is more and which is less, normally you get around 4 to 5 marks already. All right. So to me, this is a simple question. Don't lose your mark at this question. Okay. So comparing question at least got three. Question number 5, question number 6 is a comparing question. Question number 11 is also a comparing question. All right. So there's 3 questions that ask you to compare. 3 times 4 marks, that is 12 marks already. That is a variable 12 marks. All right. So is there any question that you guys want to ask me? Any question that you want to ask me? If no question, that I am going to end refraction of wave and also diffraction of wave right now. All right. I'm gonna have give you guys a break for the form 4s. Form 5, you still have another lesson tomorrow. We're not gonna be having any lessons on Saturday, Sunday, and probably Monday. I think Monday you guys are going to go for coming back from holidays or whatsoever. So we're gonna continue back on Tuesday with the form 4 first. All right. So if no question, then form 4, Merry Christmas. I'll see you guys next Tuesday. Form 5, I'll see you guys tomorrow. All right, that's all from me today. Good night, everyone.
Thanks, Cher. Merry Christmas, Cher.
Thank you, Cher. Merry Christmas, Cher. Have a
Thank
nice
you.
holiday.
Thank you.